But thank you everybody for attending. I hope you enjoy the webinar today. And thanks to Professor Erdemir for agreeing to do this. Really, I mean, it's the speakers are donating their time to give these talks. And we really appreciate it. So just a little background. If you haven't attended one of these webinars yet, this is named after Ralph Beard, and he came with this idea of creating this minor at Auburn University in 2012. And they created a fund for excellence at the university named after him, but he passed away a few years ago, unfortunately. So this webinar was named after him because the program that we have at Auburn would not be here if it wasn't for what he did. But we plan to do this or hold this webinar the first Tuesday of each month at 1 p.m. Central Time. And next month will be Harpal Singh. He's a sentient science, and it'll be April 6th at 1 p.m. So that's the first Tuesday of April. And he's going to talk about the exciting area of wind turbine performance in tribology. I think that'll be a really interesting talk, and it's a really important topic nowadays. So I hope a lot of you will also attend that as well. Just a little bit about the program. So what we're about, we have an undergraduate minor. It takes about 15 hours of courses for the students to complete. We also have an online graduate certificate now that's available for people in the industry. So if you want more information about that, there's links here where you can contact me at the university. I'm Rob Jackson. We also have an advisory board, and really I should thank them because they were the ones who came with the idea of this webinar. It was Raj Shah, Maureen Hunter, who are the co-chairs of our advisory board, and they add a lot of experience from the industry to what we're trying to do. Because really this whole idea came from a need from industry to provide more undergraduates with education in tribology. We have a number of sponsors. Most of these sponsors have helped support scholarships for students, which is really how we encourage them to pursue the minor. So I'm really grateful for all the support they've given to us. And finally, and not least, I'm going to, I'd like to introduce our speaker. So it's Dr. Oleic Erdemir. This is actually our largest webinar yet, and I have a feeling it's because of our speaker, because he's so well known in the field. He's Professor and Halliburton Chair in Mechanical Engineering and Material Science and Engineering at Texas A&M University. But previously, he was actually a scientist and now is a distinguished fellow at Argonne National Laboratory. He has authored over 300 publications, and I just checked, and they've been cited over 20,000 times. That's amazing. He's a member of the National Academy of Engineering, and he's previous president of the ITC and the STLE. And he's a fellow of STLE, ASME, AAAS, AVS, ASM. His work is really broad in tribology and material science. So I'm not listing everything here, and there's so many more awards I could list. He's had an incredible career, and I'm really honored to have him speak to us today. And so with that, Ali, you can, I think, take over.
I'm greatly honored by this invitation. Ralph was a very dear friend. Unfortunately, we lost him a few years ago. He was a tireless, unsung hero of the tribology field. And I'm glad that Auburn is actually holding these webinar series to honor him. So with that, I should also thank all of you, especially Rob and his team, for hosting these webinars to actually promote the field of tribology. I think this is quite innovative, very clever. We have to educate ourselves. I think we have to get more vocal on the importance of the tribology for our society, for our sustainability. And this is great. So I'm truly honored. So today, I'm going to talk about vanishing friction. And this subject also well known as superlubricity. You know, in other fields like material science, we have, you know, superplasticity, or in the physics, superconductivity. These mean something extraordinary. In our field of tribology, I think one of the most important desire is to reduce friction as much as we can. And also, of course, wear. Friction and wear go hand in hand most often. Especially friction tends to be very tricky. It's something that we have been working on for maybe you know, over 1,000 years. But we are still working on it, and because of the fact that it is so intriguing, so intertwined, it's very difficult to, you know, take a good handle of it. So let me first introduce my outline. So first, as part of my presidency as of the International Tribology Council, I want to draw a very strong parallel between friction, energy, and environment. These are indeed very closely related. So if we can somehow vanish friction, I think that will really have a huge impact in our energy security, in our environmental viability, and ultimately the sustainability of this planet as a whole. So I'm gonna speak a little bit about what makes and breaks friction. You know, what are the major mechanisms of friction, and then I will try to introduce some of these atomistic level understanding of superlubricity, or how we can actually vanish it. And there have been some very interesting studies related to the latest development in 2D materials area, and the codings actually have been around. And then I will also talk about future directions as to, you know, where all these studies might be heading, and finally conclude the talk. So friction, as you all know, is known as resistance to sliding. And we feel it, actually, we live with friction every day. We hardly, you know, make a big deal about it, but it's our daily, part of our daily life. As I mentioned, despite its being part of our life, it is one of the least understood physical phenomena. I mean, we are doing all we can with all these computational capabilities to understand the root causes of friction at atomistic level, and we are making progress. But have we actually fully understood it? I doubt so. So it's going to be with us for quite a while longer. And it is very important for safety, safe walking. A few weeks ago, actually, we had a big snowstorm here down in Texas, and it crippled life, and everything almost came to halt. And you know, it caused a major damage. People fell down, actually fractured their legs. I have a friend at the university actually had a major surgery because of the fractured, you know, hip. So it's due to friction or lack of it. So, and friction also is a major source of lost energy. In order to overcome it, we have to, you know, spend energy. So that's very important. And of course, most of these energy that we use to overcome friction comes from a power plant, and most of these, unfortunately, are powered with fossil fuels. And when we burn these to produce power, of course, we produce a lot of CO2 and other hazardous emissions, and these are not very good for our environment and for our sustainability. And believe it or not, vibration, heat, sound, sweet sound of a violin or cello, static electricity, light, touching and feeling, all these things actually relate to friction. So it is a major part of our daily life, industrial life. In a nutshell, it has its roots at atomic scale, as this diagram shows, but its consequences are felt at the engineering and societal level. So there are various levels of, hierarchical situation where we see friction and feel it. And also at global scale, as I mentioned, it has major ramifications in terms of our energy and our environment and sustainability. If you go to the next slide, you will see that worldwide, we produce huge amount of energy. We need it. We need it for our industrial activities and modern lifestyle. There are so many of them. And in every one of these, there are a lot of moving parts, as you can imagine. I mean, some of these activities, industrial activities shown down here, shows the fact that there are a lot of moving parts, and every one of these, there are frictional interfaces where energy is dissipated. And with Professor Holmberg from VTT Finland, actually, we tried to estimate how much energy is lost to friction on all these industrial activities. And it turns out that if you combine the portion that is due to wear and material loss, so the friction and wear almost consumes quarter of the global energy output. And this is quite incredible. And collectively, these two events actually also produce 8 gigatons of CO2 emissions. I think currently total CO2 emissions about 44 gigatons of something. So it's almost proportional. It's quite a huge amount of CO2. And this has been actually going on for very long. And this accumulates in the upper atmosphere, and then we create this greenhouse gas emissions. And then we have all these weather-related or environmental related issues. So if we could hypothetically or fictitiously, if we could actually reduce or even possible vanish friction in all these industrial activities, I mean, environmentally, I think we will be in a very sustainable, very clean, very healthy, situations for a very long time. But unfortunately, we are very, very much dependent on non-renewable energy resources, and these are mostly fossil fuels, and I think this will continue well into the second half of this century. There are a lot of good activities for clean energy resources, but these developments are, unfortunately are at very slow pace. So if we can actually look at briefly the situation with transportation vehicles, especially in this country, I mean, we have almost 300 million of these moving in our roads. And this way of transportation actually became extremely inefficient, very wasteful in terms of energy. We did a very focused study with Professor Holmberg to see how much of the total energy that we put into our, or the fuel that we put in our gas tank is actually used to move the car. And it turns out that if you take all these hydrodynamic losses and the air drags and all these other things, bottom line is that only about 20% of the total energy that you recover out of these fuel is used to move the car. And this is really unsustainable. I mean, this had to change. Of course, nowadays, there's a huge interest in switching to electric vehicles, and these are actually coming very strongly. And hopefully by the middle of this century, half of the vehicles on the road hopefully will be powered by electric vehicles. And I think that's a great thing. In this country, as you can imagine, every one of us, according to the statistic from the EPA, we drive a car and we are culprit in terms of our carbon footprint. And every one of us actually produce almost 4.5 tons of CO2 on an annual basis. And when you think of it, the fact that we have over 1 billion motor vehicles, I mean, these are quite unbelievably high numbers. In this country, we have very huge transportation, number of transportation vehicles, and collectively they are blamed for 28% of the greenhouse gas emissions in 2018. So as I was saying, these are not very good in terms of our future sustainability and future generations, and we have to do something about it. So with respect to the electric vehicles, actually we did another study with Professor Holmberg, which shows that if we switch to battery-powered electric vehicles, we can actually improve the efficiency by 70%. Here we compare the situation with an internal combustion engine based vehicle versus battery electric vehicle. And as you can see, I mean, the gain in efficiency is quite remarkable. I think this is the way to do it. But in terms of their carbon footprint, it may not really be much difference. If we still get the power out of these fossil fuel burning power plants, the situation will not change. Its only change will be to the fact that we are burdening that carbon footprint to another source, as opposed to the cars or the vehicles that we draw at the moment are the main sources of these greenhouse gas emissions. So it will be burdened, or it will be shifted to a coal-powered or natural gas-powered power plant. So these are the kind of things that we have to be very mindful. So in general, if we can somehow switch or develop technologies that will enhance friction or reduce frictional losses, so that will have a huge impact in the environment, and also in terms of energy security and sustainability. So historically, if you look at how friction science and technology evolved over the years, so we have come a very long way. I mean, the early studies, I think the scientific studies goes back to Middle Ages. Leonardo da Vinci was, of course, the master of these early studies, and he actually developed some very sound, scientific principles that resonate even today. I mean, his experiments could be duplicated today, and you practically get the same, results. But since then, we have made remarkable progress, especially in the beginning of this century, with all these atomic scale models, but Tomlinson and Frankel and the others, which then took further on their footprint and came up with some more realistic, models in which the possibility of vanishing friction actually became possible. Hirano and Sokolov were specifically two pioneers of these early studies in which they developed these commensurability versus incommensurability states of contact, which will actually make a huge difference in the frictional properties of two contacting surfaces that I will mention later on. Later on, we increase or enhance our knowledge further, looking at the electronic and phononic dissipation or the sources of friction. And based on those understanding, coming up with all these latest and greatest materials, especially 2D materials and surface modification technologies, which now made it possible to actually achieve superlubricity or nearly zero friction at the interfaces of some sliding surfaces. So this kind of summarizes the progress in superlubricity for solid sliding surfaces. So it looks that we have really come a long way. And we all know that if we rub steel against itself or aluminum against itself, we get very high friction. If we sprinkle some boron nitride or graphite or PTFE like MyS2, friction actually comes down quite substantially. So these layered or otherwise very slippery solids make that interface very, very slick, and thereby the friction actually comes down. But since the beginning of 2000, there have been explosion in these kind of studies, perfecting these 2D materials in a more controllable manner. And thereby, under the right conditions, even seeing levels of friction down to 0.001. And these are quite remarkable. And I think that kind of shows us the way how sliding interfaces can be engineered or lubricated to achieve extremely low friction coefficients. And from a more practical point of view, of course, liquid superlubricity will be far more desirable. Not all liquids actually give low friction. If you, apply water or alcohols to a sliding interface, you don't necessarily get low friction. But then you have all these base oils or these synthetic lubricants like PAO or PAG. With the addition of these friction modifiers, the friction can actually come down. And there are special circumstances where water can actually be a marvelous lubricant for some certain ceramics. By virtue of some tribochemical interactions, that surfaces actually become extremely slick. And then we have all these other technologies related to polymer brushes, PAG, phosphoric acid, and some nanocolloidal systems. When present at sliding interfaces can also provide extremely low friction coefficients. So let's look at the cases of 2D materials. And these kind of started toward the middle of 2000s actually. And there was a discovery of graphene, which really made a huge impact in so many ways. And one of which, graphene was said to be one of the strongest material. In fact, it was said to be 200 times stronger than steel. And it turns out that it has some other properties that will also have a huge positive impact in terms of their tribological properties. So we were one of the very first actually started rubbing and scrubbing graphene. And we published some very good papers, actually a number of papers, which showed indeed even one monolayer of graphene would provide very long wear life, despite having very high contact pressure. And there was also the possibility of further functionalization of graphene to achieve nearly zero friction. And we were not the only person actually got these kind of results. And several other laboratories started working on these things. And under the right condition, these surfaces could actually provide extremely low friction coefficient. One of these conditions actually, as I mentioned earlier, related to commensurate or non-commensurate or incommensurate state of contact. These are described as, in the case of commensurate contact, you have two surfaces. They could be actually made out of the same material or similar, dissimilar material, and their atoms on the surface are in full registry in the case of commensurate, state of contact. And so, because of this full registry, you have atomic scale, strong atomic scale interactions, and thereby you have atomic, what they call atomic locking. And this will actually produce very huge interfacial, adhesion, which will make these surfaces, move with very difficulty. And in the case of incommensurate state of contact, it turns out that if these surface atoms are twisted and they were brought out of that full registry, and then you have this state of incommensurability. And this would actually produce or give rise to these weak interatomic potential, and the energy loss and gain between these atoms will kind of cancel one another. And in this particular case, you will actually have nearly zero friction. The movie in the bottom from Professor Hirano's website, which kind of illustrate these two situations. In the top, you have this full registry or commensurate state of contact. In the bottom, you have this incommensurate state of contact. And there have been a lot of studies actually with regard to these two contact situations. These are some of the only few. I think these studies are still going on. It's very fascinating. And because of the structural nature of these sliding interfaces, that is, these are, physically and structurally a very unique contact configuration. And this most often these are actually referred to as structural superlubricity. And one of the earliest verification of this was from a group of scientists from Netherlands, especially Erdemir and his colleague in Netherlands, actually were able to test this model to see if indeed one can achieve zero friction. And they used this nanoscale tribometer, which they call Tribometer, and they attach a layer of graphite or graphene to the surface of the tip, and they rub this against in the bottom to another highly oriented pyrolytic graphite. So by twisting these two surfaces, these two pieces of graphite in the other side and also on the surface, they were able to see the situation where you would actually have very huge stick slip or adhesive interaction. By twisting it slowly, they were able to show that yes, after reaching certain twist angle, you would nearly vanish friction. So this was a very interesting demonstration of the fact that this commensurate or incommensurate state of contacts are very important in terms of superlubricity and having very high friction or no friction at all. And it was not limited, this effect was not limited to very conformal surfaces. But this could also be achieved with graphene applied to a microsphere and also being rubbed against either graphene or graphite. You can see the difference in this particular article. In one case, it shows how silicon dioxide microsphere against highly pyrolytic graphite actually behaves. As you can see, with regard to increasing load, you also get very high frictional force. But if you have a graphite coating on the microsphere, rubbing against the same kind of graphite surface, the friction almost vanishes. And doing the same kind of experiments against hexagonal boron nitride also showed that, yes, the friction actually is extremely low. So these microspheres, of course, will favor incommensurability, and you will have only a few direct atom-to-atom, registry or commensurate state. In which case, you will also have this favorable incommensurate state of contact and thereby extremely low friction coefficient. Now, as I mentioned, we have done a lot of studies in this particular area. And these works were with Diana Berman, now at the University of North Texas, and my colleague, Ani Sumant, still at Argonne. And we have seen extreme wear resistance of graphene. And these graphenes could actually be produced using CVD method. Even one layer of graphene under some reasonably high contact pressure, you could actually have over 6,000, sliding cycle type of lifetime out of these graphene, sheets. If you build a few additional layers, actually that wear life would actually go all the way up to almost 50,000 cycle, and this was quite remarkable. Of course, these had to be done in a special environment. In this particular case, we are talking about hydrogen environment, and hydrogen seems to actually make the broken surfaces of graphene, of course, under sliding contact, you might actually eventually wear through or fracture through the graphene, cage. But these broken edges are stabilized or neutralized by hydrogen, so that they don't necessarily further disintegrate or participate in this stick slip type of behavior to trigger not only very high friction, but also high wear. In further studies, we have also seen that one can achieve superlubricity with graphene. These were just discrete flakes of graphene sprinkled on a surface. And then we had to combine these with nanodiamond particles, typically in the range of 3 to 5 nanometers, and rub them against a DLC-coated ball. So we had carbon material in different forms, in solid carbon in the ball side, and then we have graphene and these nanodiamond. So these combined carbon structures were able to actually bring friction coefficient down to 0.004 level. And when we did very high resolution transmission electron microscopy of these surfaces, we noticed all these scrolls like formation with diamond nanoparticles right in the center. So this kind of gave us the impression that these nanoflakes actually been attaching to the surface of nanodiamond, which actually makes perfect sense. Both edges and the surface of the nanodiamond will have sigma bonds or these covalent bonding possibilities. Once that happens, then the rest of the graphene would actually just scroll to form these rolls. And there was okay, let me see if I can. So this was actually also simulated using MD, reactive MD simulation method that shows exactly how these nanoscrolls form. Once the nanoscroll forms, actually the severity of the nanodiamonds as an abrasive particle as well as adhesive particle has been diminished. And so that they became more benign, and they could also roll in addition to having this amount of surface-to-surface interaction, or this what we call commensurate, state of contact type of situation. So there have been so many other studies that attest to the importance of these, structural superlubricity in one form to another. And graphene has been done quite extensively. Other colleagues looked at the MOS2 and other 2D material, and so on and so forth. It was also found that even in nanotubes, the similar effect could be achieved by twisting the inner and outer shells of the tube and bringing them to these non-incommensurate, state of contact situations. There have been some other exciting developments quite recently. One actually relates to this Maxine, another 2D material, and still emerging. There seems to be a lot of potential in terms of potential, industrial applications in the near future. And the fact that these can be actually functionalized by some polar molecules or additives and added to lubricant, and in that particular case too, you can achieve extremely low friction coefficient. So this sounds very exciting in terms of maybe large scale, industrial applications in the near future. Another class of material actually that shows superlubricity was these DiamondLike carbons. And DiamondLike carbons actually come in different form. And by and large, they are amorphous in nature, but depending on the structure and the chemical state, they could have, for example, as shown in this diagram on the left side, no hydrogen, mostly sp3 bonded carbon, and then you have also hydrogen incorporated into these structures. So they come in all kinds of chemistries as well as structural, order. You can have diamond-like carbon with extremely sp3 bonded, character, and these are almost similar to diamond in terms of their friction and wear properties. And you can also have mostly sp2 bonded type of carbon, and these will be similar to graphite. And then you can add hydrogen, and these are mostly produced in a hydrogen containing plasma environment, and the hydrogen actually incorporates into the structure, and then you have all these hydrogenated carbon variations. And also you can dope other metals and elements into these DLCs to achieve other type of physical and mechanical properties. CNX is a very important DLC film, and these metal dope DLCs are also very important in terms of their industrial promise. This WTC DLC, tungsten DLC, is widely used in industrial applications, and you can also build these DLCs at nano-layer architectures. So from a superlubricity point of view, there have been very many studies that shows that with different type of alloying or doping, you can actually achieve superlubricity or the friction coefficient less than 0.01. And in our studies, we concentrate mostly on these amorphous hydrogenated carbon on the left side of this diagram. And other colleagues looked at this CNX or these silicon doped DLCs, fluorinated DLCs, even sulfur could be incorporated. In most of these cases, when they did the friction studies or experiments, the friction turned out to be extremely low. In our case, we started our studies toward the end of 80s, actually, and we published, I think, one of the very first paper on DSC back in 1990. So what we did was that we have seen a very unique correlation between the amount of hydrogen that we put in the DSC versus their friction coefficient. And we further optimized these to achieve a very unique chemical composition that resulted from 25% methane and 75% hydrogen in the plasma environment. And the DSC film grown in this kind of plasma environment gave a friction coefficient of down to 0.001 level. This was quite remarkable. I mean, we could actually measure this one test after another. Not only that, but we share these films with other colleagues from other laboratories to see if they can also duplicate our results, and they all did. So this was quite remarkable. So based on our analytical studies, we came up with a model in which we said that since we put a lot of hydrogen into these films, not only their bulk, also the surfaces are fully hydrogen saturated. And we are kind of illustrating that in this particular molecular model down on the right corner. And if you look at these from a high school level chemistry textbook, and when hydrogen actually loses its single electron to carbon, then the nucleus is positively charged, neutron. So you have, when you bring these two surfaces together, it will feel like as if you are pressing two positively charged surfaces against one another. And obviously, these positively charged surfaces will trigger repulsive forces. Otherwise, these surfaces would have been actually developing, adhesive forces, and that would trigger high friction. But here, you are doing the opposite, which is, triggering high repulsive forces. And we have done some collaborative studies with several colleagues, and they actually looked into this using ab initio calculations and DFTs and whatnot. In one of these cases, what they did was that, of course, diamond is a very model system. They could easily simulate that. If you look at a diamond 001 surface pressed against another without the hydrogen present in between, and as you bring these surfaces together and after a certain distance, it's about maybe 2.75 or something like that. And these surfaces would actually develop these very huge attractive forces, as shown on the left side of the diagram here. But if the surfaces at the interface is fully hydrogen terminated, and if you do the same thing, that is to bring these surfaces closer to one another, and at a distance about less than 2.5 angstrom, these surfaces actually would start developing these repulsive forces, as shown in the bottom. So this was one of the very first simulations, but other colleagues from different places also did the similar simulations to show that indeed these highly hydrogenated or hydrogen terminated carbon surfaces will trigger, huge repulsive forces as you bring them closer to the contact situation. So this kind of corroborated as to what made these highly hydrogenated carbon surfaces super lubricious or providing this nearly frictionless, sliding conditions. And of course, we did TOFSIM analysis of these surfaces after the test. The only thing that we could see within the sliding wear track, actually, you only have carbon and hydrogen as shown in these 3D TOFSIM map. So to further prove our point, what we did was that we started with a hydrogen-free DLC. Actually, these are the kind of DLCs that you can directly sputter out of a carbon target in the absence of hydrogen. And these are mostly sp2 or sp3 bonded carbon, but on the surface, you actually have maybe some adsorbed species, and that's about it. And using a ion bombardment technique and using these hydrogen atoms ionized and bombarding these hydrogen-free carbon surfaces. And then we felt that if we can actually do this, then these highly hydrogenated or artificially hydrogenated carbon surfaces should also give superlubricity. So we did the experiment, and it was no surprise that hydrogen-free or non-hydrogenated surface actually would fail after about 5 to 10 meters, and with a very high friction, typically going all the way up to 0.85 and higher. But after the surface is fully hydrogenated through this hydrogen treatment or bombardment, and that surface started giving this extremely low friction coefficient as shown in the blue curve. And in fact, we could measure the friction coefficient down to 0.005. So the hydrogen termination of these carbon surfaces or these DLCs turned out to be a very important mechanism to achieve superlubricity. And of course, this also reflected very well on the wear of these materials. In the case of non-hydrogenated or hydrogen-treated surfaces, DLC film actually was worn out very quickly. In the other case, plasma hydrogen-treated surface, you could hardly see the places where the sliding had taken place. So extremely low friction coefficient also resulted in almost zero wear. And similar things could be achieved with these highly polar oil additives. One is the oleic acid. This is a highly polar molecule. And if you put it with a base oil on the surface of the DLC, these could be actually either hydrogenated or hydrogen-free DLC, and they tend to attach to the surface. With that attachment, the surface again terminated with something more benign and less, chemically active. And with that, you could actually achieve extremely low friction coefficient as shown in the red curve in the bottom. So in the case of DLC, it looked at as if the superlubricity has a lot to do with the hydrogen termination of the top sliding surfaces. You can also terminate these surfaces with OH or in oxygen, which are not shown here, but we also did tests that were run in pure hydroxyl ion or pure oxygen. The friction coefficient would be low, but not as low as hydrogen, mainly because even these oxygen or hydroxyl, terminated surfaces would have some polar activity and attraction, and thereby their friction would be higher. If there's no hydrogen at the sliding contact interfaces, this will be very typical of tetragonal amorphous carbon that is actually produced from a carbon target, either in a laser, pulse laser deposition, RPVD, or sputtering methods. And those surfaces actually will give you very high friction, mainly because of these pi and sigma bond or covalent bond interactions. So DLCs actually made a huge impact, industrial impact. They are used in all kinds of industrial applications. Some of them are actually summarized here, and quite recently we published a book that kind of looks into all these latest and greatest coating technologies for vehicle applications with a friend from Hyundai company. So in terms of overall progress toward achieving macro scale superlubricity and their application from these very early ages where the Egyptians actually struggled to mold these huge clusters with hundreds of slaves, we have come a long way. I mean, We have done quite remarkably well in terms of understanding the origins of friction. And with that understanding, we have developed new methodologies and new technologies, new materials, which would actually provide extremely low friction coefficient. And we are still working very hard. In fact, studies related to superlubricity quite recently skyrocketed. I think in a given year, we have now hundreds of papers published on the subject. And with all these developments, I'm very hopeful that in the future, given another maybe 10, 20 years, we might actually see some real tribological systems, utilizing some of these technologies and achieving almost, near zero friction, and with that also consuming very least amount of energy. Especially if you can somehow figure out future electric vehicles, for example, consuming very little energy due to frictional, dissipation or frictional energy losses, and that energy is coming from sun or from wind or something like that, and these vehicles will be totally green, and that will actually make a huge impact in the sustainability of our planet. So we have been very active in this area. We published a book back in 2007 on superlubricity. And since then, we actually updated, and this has been published a few months back. That contains a lot of new material, which I could not cover, but these are some of the topics that are very extensively covered in this new book that might be of interest to those people who are interested in this topic. So in summary, I think we have made great progress in the design of some new and more exciting materials, coatings, that can provide very low friction and wear. And especially these 2D materials have made a huge impact in terms of vanishing friction. And DLC has been around, but there are still a lot of work going on in this area. And I think there might be some additional new highlights or new discoveries related to their superlubricity and broader application possibilities. And in the case of 2D materials or crystalline materials, it looks that the superlubricity is pretty much dependent on the incommensurability or the scroll formation mechanism that I mentioned that we discovered at Argonne National Laboratory. And these are mostly for the 2D materials. For the non-2D amorphous materials like DLC, I think surface termination or surface termination state of these material, especially with a gas or with a molecule like hydrogen, it seems to be extremely important. And regardless of all these things, friction still continues to consume 20% of the global energy output. And this is, I think, proportional to the amount of CO2 that is released to the environment. So I think as tribologists, we have to really double our efforts to further reduce friction and thereby its adverse impact on energy, environment, and global sustainability. So with that, I thank you all, and I have had the great pleasure of working with a lot of great people. I must particularly acknowledge Professor Holmberg. We had multiple papers that relates to friction, wear, and their impact on energy, environment, and sustainability. And of course, much of my work at Argonne has been funded by U.S. Department of Energy. I'm very grateful for their generous support. And also I had one of the very best, scientists, some of the very best scientists in my team inspire me and help me actually realize all these great studies that we have published in multiple papers. And also I had a lot of international collaborators, again, which helped me with my work all along. So with that, thank you very much. And if there are questions, I'll be more than happy to answer.
Thank you, Ollie. Everybody's muted, so they don't hear any applause, but there would be an applause. There's a few questions in the chat. So one of the first ones was, how stable are the hydrogenated DLCs in an oxygen, air, and atmosphere?
That's a very good question. Not very stable. Actually, if you run these highly hydrogenated DLCs in oxygen or even in water, in open air, you don't necessarily get very low friction. The wear could be still quite good. There are a lot of tribochemical interactions between oxygen in the environment and the surfaces. Of course, oxygen can easily react with both hydrogen and carbon, and that creates actually oxygenated, tribolayer, which is not necessarily very easy to shear. So these hydrogenated DLCs are meant to be for inert environment, for vacuum environment. Of course, for hydrogen, actually, we did a lot of work with these coatings in a hydrogen, bearing environment for some fuel cell applications. And we also got very good results in methane, as these might be used for some compressor applications.
All right. There's a question about the load. It's kind of a long question. On the slide, you showed the frictional behavior of the hydrogen plasma treated DLC where friction is as low as 0.005. Those tests were done at loads of 0.5 newtons. Can you comment on why that load was picked, and also what happens if you increase or decrease load?
That's also a very good question. The friction coefficient actually will remain around same number, but the lifetime of that hydrogenated surface or that low friction regime will shorten if you have to go to 5 Newton or 10 Newton. After all, that hydrogenated top surface is really very thin. We're talking about maybe less than a nanometer or maybe up to a couple nanometer. We haven't really modeled this, but that hydrogen was actually hanging on the surface, and some of it may have also incorporated into that surface in the atomic form, but by and large, it was mostly hydrogen bonded to the surface of that non-hydrogenated carbon.
I think the second part of that question you already answered is about the environment and the exposure to the air. So let's see what else we have here.
Yeah, I mean that non-hydrogenated or hydrogen-free DLC actually would work better in open air, where you have water molecule and you have oxygen. These would again interact with that surface tribochemically to produce a easily shearable interface. But that surface will not necessarily give you superlubricity because that hydrogen, the oxygen termination or hydroxyl termination of that surface will still trigger these polar, activities across the interface, and that thereby the friction coefficient probably will be around 0.1 to 0.05.
So how much time do you have? We're through an hour, but there's a few more questions.
Sure, I can stay around, no problem.
Okay. What materials show the most promise for achieving near zero friction, as well as high durability in macro scale applications involving dry sliding in ambient environments?
Well, that's a dream. I cannot really say. Actually, that sulfur dope DLC, for example, my colleague from Northwestern University, Professor Yipia Chang, actually did a lot of work on that. That particular DLC happens to be benign to environment. And something like that, I think, could potentially work quite well. What else? I mean, so unfortunately, in the open air, you have water and oxygen molecules available, and these unfortunately interact with that surface. So again, that the interface, that sliding contact interface is really very active, not only physically, but also chemically. And all of a sudden you see all these molecules being dragged into these tribochemical reactions or interactions. And the products are more often not easily shearable, and thereby you don't necessarily get low friction.
How does a heteromaterial surface compare to the hydrogen treated?
I think heteromaterials, have their superlubricity mostly related to this higher degree of incommensurability. So it's easier to achieve on them than if the surfaces are made out of the same type of material. So that gives some advantage to these kind of heterojunctions or hetero interfaces. But of course, for them to provide ultra low friction, you have to not only attain that incommensurate state of contact, but also maintain it throughout the sliding regimes. In that respect, there might be some challenges. But other than that, I think the hydrogenated DLCs, if you could actually have another form of termination that would make these DLCs benign to oxygen or water molecules in the open air, that would probably answer the question the previous gentleman or the lady actually asked. So probably that opens up a very interesting possibility for future studies. In fact, we are trying to do some of these, how we can actually maintain the inertness of that interface in terms of not being affected by water molecule or oxygen or some of the other things in the environment. Yet you still have these very favorable repulsive forces being also available to that interface.
All right. Not sure of this question, but it says how affect DLC, the lubricant for oxidation steps. I'm not sure exactly what. If you can decipher that, but something about DLC and the lubricant and oxidation steps. Maybe we'll go, if you know what they're talking about, you can take a crack at it.
Yeah, I mean, of course, those DSC films that I mentioned as being used for industrial applications or automotive applications, they all actually operate in a lubricated environment. And most of these DLCs actually are made of mostly sp3 bonded tetragonal amorphous carbon, or these are typically produced by arc PVD or something like that. And for one thing, these are extremely hard, and also the surface can easily be terminated with hydroxyl ions if they are available. And using friction, organic friction modifiers or these GMOs or glycerol, for example, will actually do the job in producing a surface that is benign. and fully terminated with OH or some other similar, ions, and thereby these surfaces actually will have very low friction coefficient. In fact, one of the reasons they are using these in automotive, and with the right kind of additive in the oil, GMO or something like that, organic friction modifiers, you are reducing friction actually even under severe conditions. I think I gave you one example, down to 0.01 level. I think that's quite remarkable. So these are possible. I mean, the DLC provides the flexibility in terms of, what kind of surface or the surface termination you want to have in the end. As I mentioned, they are easy to dope or alloy with other elements, and that alloying actually provides a very special, surface condition or property that in the end provide very favorable friction and wear properties.
I think there's some DLC being used in rings in combustion, in the piston, ring in the combustion engine, if I remember.
That's correct. Yes. Yeah. Yes.
Another question is, can DLC layer be possibly disrupted in course of sliding at higher loads? I think that's similar to other questions. And something is my own question. We talk about loads, but really it's like pressure. It's how high is the pressure, right?
Yeah, I mean, DLCs are amorphous, and also, unfortunately, their fracture toughness is not really very good. If the pressure reaches the point at which the substrate will deform, according to von Mises yield criterion or whatever, and that deformation will actually fracture DLC. So one has to be very careful in terms of how much pressure or load you can apply to these surfaces. Once it fractured, of course, the fragments being extremely hard could easily cause third body wear or these abrasive wear situation that might actually be counter active in terms of industrial applications.
You still ready for more questions? There's a few more.
Yeah, sure.
Okay. This next one is, do you think graphene flakes will chemically react to ferrous metals under extreme pressure conditions to form chemical film or amorphous DLC type film?
What kind of metal? I'm sorry, I missed that part.
Ferrous.
Ferrous?
Yeah.
Okay. Yeah, I mean, graphene, I think, is a very stable structure. I don't think it will further fragment or turn into atomic form so that it can actually diffuse into the iron. Whether it will actually react with that surface in some chemical fashion is possible. On the edges, of course, you have these free bonds that can interact with iron, for example, forming some sort of iron carbon bonding, as there is iron carbides, for example. But as a stable, coherent, flake or substance, I don't think it will dissolve or it will react with the surface of iron, in my opinion. But of course, one has to be very careful when you bring two solid surfaces, very close proximity. Then you start triggering all these van der Waals bonding, electrostatic bonding. They will interact at some fashion, but from a chemical point of view or chemical bonding, that may not be that easy.
And by the way, you have lots of people saying thank you in the comments. So here's another question. Is interesting looking at the electron-rich repulsion of the graphene example in coefficient friction compared to the electropositive repulsion of the hydrogen-treated surfaces. Which do you think would be more stable for real-world applications?
Again, the hydrogen-terminated carbon surface will have its limit. Those surfaces are stable only in inert or vacuum type of environment. I mean, under static conditions, actually, nothing happened to them, but under dynamic conditions, you trigger tribochemical reaction with the oxygen and water molecules, so that kind of, you know, that surface become destroyed. But from I think graphene stability, in my opinion, will be far more higher, because the cage of the graphene is, as I mentioned, supposed to be extremely strong. In fact, you know, there were some claims that the graphene is the hardest material and also the strongest material. So breaking that cage, you know, will not be that easy. Of course, under extremely high loading conditions, everything will break. But despite being only one atom thick or few, you know, layer thick, these surfaces tends to be extremely, you know, stable. In fact, we have done a lot of studies with this. Kalyan, I think, is in the audience, did some of these experiments. Diana, I think the other colleagues in my group at Argonne, we did all these studies to show that under even extreme conditions, when you do the Raman after the test, you can still see very strong signal from the graphene structure itself. Eventually, these things, of course, you know, become highly unstable or turn into very tiny nanoscale, you know, clusters. But nevertheless, until that point, you have a very long wear life, or you can put a lot of pressure before they are fractured.
All right, thank you, Ali. I think we actually got through all the questions.
All right, thank you. Thank you again. I really appreciate the opportunity, and I'm glad that I could do this. And this is a great way of honoring Ralph, and I'm glad you guys are doing it.
You have a couple books to buy. Your books?
No, I mean, I hate to.
No, I need to get copies
things,
of them.
but you know, there are some very good information. Actually, we spent almost 3 years to get that last book actually going with Professor Jean-Michel Martin and Professor Jianmin Lu. You know, the whole thing actually help the field and help to the tribology, you know, community. That was the whole idea there.
This is the T-shirt I'll be sending you.
Okay.
So I'll send that to you.
Thank you.
I'm not sure when I'll get there, but I really do appreciate you doing this. And you know, hopefully I'll see you in person.
Thank you, Rob. Thank you. Thank you, everybody. Appreciate it. Yeah, thanks for joining the webinar.
Thank you.
Bye-bye.